Our topic for tonight is meteor detecting. Now, this is a project that anybody who can work a hacksaw and do a bit of basic woodwork and a little bit of computers and a little bit of connecting wires together can do. It's not a particularly difficult project. But the fantastic thing about meteor detecting by radio is that we can do this at any time of the day or night. So it doesn't matter if it's dark, it doesn't matter if it's cloudy, if the weather's not cooperating. This project will let you do some astronomy regardless of the conditions. And really, the project will cost you somewhere in the region of £50 to £60. The most expensive item for the project is actually a little radio dongle that you can pick up off Amazon quite easily. The rest of the bits and pieces you can actually get from around the house. So we'll talk about that in a bit, but we need some plumbing pipe, a bit of woodwork, and a little bit of wire again, which we can get off Amazon. Literally, if you can't even get hold of plumbing pipe, I have made one of these antennas that we will need to make out of a tape measure, believe it or not, a steel tape measure, just cut up into pieces, will work fine. So pretty easy to do. Now, this isn't my project. This is something that Paul Hyde of the BAA came up with a few years ago, and he actually put all of the details in the Sky at Night magazine, and very helpfully the BAA at their website actually the whole article is available. It's in two parts, actually how to build the project and how to set the basic software up. We'll talk through it and some of the practicalities, and we'll have a look at some of the details setting the software up in a bit. So really not too intimidating, but as I say, if you just need to get the details, I'll give you the website address again. It's here. It's www.britastro.org/radio downloads. If you go to their site, you'll be able to find it. If not, I'll also give you a link to my website at the end of the talk, where we can actually get all of these details as well. So this is a fairly straightforward project. Really, the basic premise of the project is to actually be able to detect a meteoroid that enters the atmosphere using a radar detector. Now, what's a meteoroid? Well, a meteoroid is just a little grain of sand or a piece of rock that's travelling around in the solar system. It enters the atmosphere at very high speeds as it crashes into the Earth. So they can be travelling anywhere up to 160,000 miles an hour. Now, if you were travelling at 160,000 miles an hour, you'd be able to leave Essex and end up in Australia in about 4 minutes. But just like the meteor, you'd cook yourself to a crisp. Now, so what happens is the meteor is travelling happily through space for millions of years, and suddenly the Earth comes along and gets in the way. And when it hits the upper layers of the atmosphere at heights of somewhere between 120 and 80 kilometres up, there's very, very little air up that high, but there's enough to actually start impacting the meteor. And what happens is it creates a shock wave as it crashes into the atmosphere, and that heats the air up. The air gets compressed, just like if you pump up a bicycle pump up your bike tyres, and then you feel the end of the bicycle pump, the end of it gets really hot. That's because you compress the air and that makes it hot. Same thing's happening with the meteor, but it gets much, much hotter. So the meteor gets really hot, and as it gets hot, it then creates this glow. So we can see a meteor as a shooting star going across the sky. We can see those most nights sporadically, and then there are quite often meteor showers going on, where you can see lots of meteors in an evening. As I say, most of these meteors are the size of grains of sand, but they're going very, very fast, so they travel at really high speeds. Now, what's going on is that the meteor is actually ripping the air molecules apart, so it's stripping electrons off the atoms. So the air molecules are made of protons and electrons, and the electrons are ripped off by the heat that the meteor is generating. And as the electrons are ripped off, they then are free to move around. And as we'll see, that allows them to reflect radio waves quite efficiently until they recombine with the meteor, with the protons in the atoms. And when they recombine, they have to get rid of the extra energy that they've gained through the heating process, and they give off light to do that, which is why we see a glowing trail when a meteor comes through the atmosphere. It's that extra energy that the heat has generated. The electrons heated up, they escape from the atoms, they join back to the atoms later on, they get rid of the heat as light. The same process happens in lightning, but electricity heats the air, but again it rips the atoms apart. The electrons get separated from the protons, and when they recombine they give off a flash of light. So it's the same process, just a different mechanism. So conveniently, as I said, what's happening is these meteoroids enter the atmosphere at anywhere up to 160,000 miles an hour, and as we can see here in this diagram, the meteoroid, this little grain of sand, is zipping through the air, and it creates a trail where the protons, the red things, the centers of the atoms, have been separated from the electrons, the blue things, and while the electrons are free, because they're quite light, they'll move around, and that causes them to reflect radio waves. So as you can see, what we have down here is a transmitter that's giving off some radio waves going up into the sky. When it hits the trail where the meteor's been, it will reflect those radio waves back down towards the ground, and in all directions, in fact. So there are two ways in which that can happen. The first process is called backscatter. Now this is sort of the process that radars use. So if you're using a radar to track an aeroplane, the radar sends a signal out into the sky, a radio wave into the sky, and then it hits something. In the case of an aeroplane, it'll be the metal aeroplane, and that will reflect the radio wave back in lots of different directions. In the case of a meteor, the same thing happens, and what we get is backscatter, what we call backscatter or diffuse scattering. If you imagine getting a torch and shining it on a wall, a matte painted wall, the light scatters in all directions, and the same thing's going on here. That's called backscatter, and that's conventional radar. Now that's quite convenient for tracking meteors, and it's been used since the 1950s, shortly after the invention of radar in the war and for the Second World War. They discovered they could track meteors, and the handy thing is you can time, if you send a pulse of radio waves out, you can time how long it takes to go out and how long it takes to come back, and that lets you know how far away the thing the radio waves are bouncing off is by the timing, and also you can check the frequency change and you can tell how fast the object is moving. But you need a really big transmitter for that to work. It's quite expensive, not something that's very easy to build as an amateur. It would probably be beyond our capabilities. If you're sort of running the university science department, you probably could do it, but as an amateur, it's pretty difficult to do. Fortunately, there's a second way that radio waves can be reflected off meteors, and that's called forward scatter. And in this case, we've got a receiver. Again, it's beaming a radio wave into the sky, but this time when it hits the meteor, the beam is reflected like it's bouncing off a mirror. So if you imagine shining a torch into a mirror, the beam hits the mirror and it bounces off and carries on in sort of a single direction. And this is called this angle of incidence and reflection. You may remember it from sort of school physics. Basically, this angle here is the same as that angle there with respect to the normal, i.e. 90 degrees to the surface the radio wave is bouncing off. Now, in order to detect a meteor, what we can then do is we can transmit a radio wave, so it's coming from the transmitter over here, bouncing off the meteor and then being picked up by the receiver. Now, the radio waves are going in all sorts of directions, so it's not very helpful because most of the time you've actually got to pick up these radio waves. But if we do something clever, if we actually put the receiver and the transmitter far enough apart, then the direct path of the radio waves from the transmitter to the receiver is blocked by the curve of the Earth. But when a meteor enters the atmosphere, it's suddenly able to bounce the radio signal from one over the curve of the Earth back towards the receiver. So when you can't receive the transmitter, you know there's nothing going on. When you get a ping of radio waves coming from the transmitter, you know there's a meteor up there. Now, just to be clear, both of these processes, backscatter and forward scatter, are happening all the time at the same time. So I've just separated the two diagrams here just to make it clear what's going on. But any transmitter is going to have a forward scatter and a backscatter element. It's just the receiver that determines which one we're picking up. Okay, so that is, that's the basic idea of how to detect a meteor using radio waves. Now, the average height of a meteor is about 100 kilometers up. So as I say, sort of 120 down to 80. So it's 100 kilometers up. So anywhere so from here in Essex, say here we are down in Essex, at a height of 100 kilometres, the radio horizon, where we imagine if we send a line out from us to the sky, is about 1,150 kilometres in size. So imagine this is a circle. It's not a very good circle. I drew it in Google Maps, and it's not very good for drawing circles. But imagine this is a circle. It's just over sort of 2,300 kilometres wide, so 1,150 in radius, and that's any meteor that enters this circle we could potentially detect. Anything that's outside of this circle will be over the Earth's horizon from our point of view. We wouldn't be able to see it. Anything inside the circle, we can see it. Now, what we used to do in the old days is we would then find a TV station, an analog TV station, if you remember those from the old days, and we just need to find a radio station that is far enough away that we can't pick it up, a TV station that we can't pick it up normally. So it's going to be several hundred, several thousand, a couple of thousand kilometers away, but that we can both see the same bit of the sky. We'll have a look at a bit more of that in a minute. The problem is that since we've moved to digital TV, the digital TV transmitters don't really work very well for this project. So we need a different source of radio waves, which we'll talk about again in a moment. Okay, so we talked about where's this transmitter going to be. Well, okay, if we imagined that we were here in Essex and we had an imaginary transmitter down here in Gibraltar in Spain, the radio waves from the transmitter are going into the sky, and at 100 kilometres up, this is how far they would reach from the transmitter. And from Essex, we could see this distance into the sky, and the bit where the two circles overlap around the transmitter and receiver, just like a Venn diagram, any meteors that went through that bit of the sky would be able to be detected by bouncing the radio waves off the meteor from the transmitter to the receiver. So just to make it a little bit clearer, so we've got this little sort of animation here of the Earth, and we can see again this imaginary transmitter and this imaginary receiver that we've got. So basically, here we are in Essex, the green circle. Here's our receivers here. Here's our transmitter in Gibraltar. You can see the radio waves at 100 kilometres above the Earth would travel out to this distance, and we would all be able to see them out to this distance. So the area where they both overlap, this area here, any meteors that went through this bit, we would be able to pick them up by seeing the reflected radio waves. Okay, now we're not going to have a transmitter in Gibraltar, but we are conveniently going to have one in France. So there is actually a really convenient transmitter in France, and this is the Graves military radar. This is operated by the French military. They've got this big transmitter down in Dijon, near centre of France, and it's actually used for tracking satellites. So they want to see what satellites are passing over them. So they send radio waves out into the sky, and they have basically a continuous transmission covering about 180 degrees. So imagine half a circle facing due south. Anything that passes through that area that is between 15 degrees and 45 degrees up in the sky, 40 degrees up in the sky, anything that passes through that circle, their radio waves will bounce off and they'll be able to pick it up. Let's have a little bit more of a look at that. Now, as I say, this is a top secret military site. So I've actually managed to get a picture of it here. You can see this is basically the transmitter array. So it's made in four sections, like a sort of half circle. This is sort of pointing, this is due north, so you imagine it's pointing behind us, due south, the radio waves going out in a sort of half circle from east through south to east through south to west. If you go onto Google Earth, you can find there's this lovely old military airfield near Dijon, and guess what? They have actually blurred it all out here. So you kind of look at the Google Earth satellite picture, you can't see it's there, but you can see these sort of white blobs. Give you a bit of an idea of what's going on, and there is actually a picture of it. So this is their transmitter for tracking satellites, so it's top secret. They actually have a receiver station, which is down near Marseille on the south coast. And this is the Google Street View of that receiver station. You can see it's all been blurred out. I think we can safely assume that there's no tea room and visitors definitely are welcome here. But we don't need to worry about this. This is what they use for tracking the satellites. We're not interested in that. We're only interested in the transmitter. Now the transmitter transmits on, I'll just nip back here, 143.05 megahertz. I'll explain what that is in a little bit, but that's a radio frequency. So say BBC Essex is on 103 megahertz, so it's not that much higher up in terms of frequency than normal radio stations. It's actually quite close to the frequencies that radio amateurs use for their radio hams. They use their transmitters, which makes it very convenient because there are lots of designs of antennas and other equipment that can quite happily receive this frequency already in existence. So that's really useful for us for our project. Okay, so moving on. Now what's happening, this is again a top secret video that we managed to get hold of. I'm joking, it is on the internet somewhere, but it's not great quality. I think it was filmed by some guy with a mobile phone from some kind of military sort of recruiting truck at an air show, so it wasn't the best quality. But what you can see is going on here is this is the transmitter near Dijon, and what it's doing is it's beaming these radio waves out into the sky in this half circle between 15 and 40 degrees up, but it's actually sending out 4 beams in different directions at the same time. Remember, we have those 4 transmitter panels. Each one is sending a beam, and it scans backwards and forwards in its quarter of the half circle. So it's an eighth of a circle, eighth of a circle, eighth of a circle, and it scans backwards and forwards. So it's not quite continuous, but it's continuous enough for our purposes to detect meteors. So it beams stuff out into the sky. It is scanning. It is allegedly top secret, but we know all about it. Now here's a map. So here we are again up here at the top. We're in Essex. Transmitter is here. The receiver that we talked about that they use for the satellites is down there, but we're not interested in that. And what's actually happening is that the radio waves are beamed out in this horseshoe. Now what you've got to imagine, this is half a sort of donut. So the yellow is the top of the donut and the green is the bottom of the donut. So this is a volume of the sky, and this is the heights that meteors travel at, so between 120 down to 80 kilometers above the ground. Any meteors that pass through this volume can be picked up by us using this transmitter. Also, we can pick up the International Space Station. If it travels through this purple area, it's much higher up, so you can see it much further away because it's not below the horizon. Again, just to try and make it a little bit clearer, got a handy little animation here to show you what's going on. Again, what we've got, just wait for it to come around. So we're up here in Essex, transmitter is down here in Dijon, and you can see, like I say, this sort of weird half donut shape. Anything that passes through this volume of a meteor passing through this volume, we can pick it up. Space station is much higher, it's not this big, obviously it's not scale, but the space station passes through this area, we can detect it. We can also detect lots of other satellites, so we've been picking up lots of Starlink satellites recently. You can get lots of pings off those. It's not the total story, to be honest, because actually it's very hard to send radio waves in only one direction, and we know that there's quite a lot of radio transmission from this transmitter in the northern part of France as well, in northern Europe, because we track the space station using it, and we can pick it up when it's over this bit of France, which is not where the radar is pointing. It's behind the radar, but the radar does send lots of radio waves backwards. So very easy to pick up. Any part of this area is sort of visible to our radio receiver in Essex. The further north you go in the UK or Europe, you're going to start seeing less and less of this area, so you're going to pick up fewer meteors. But on the plus side, there is actually a possibility of picking up stuff in the northern area as well. And we know certainly people as far as north as sort of Newcastle and Scotland in the UK, where theoretically they shouldn't really be able to see this area because it's too far below the horizon. They can still pick meteors up. Okay, so that's the basic idea. Now, how do we do it? So we've got this multi-million-pound space radar that the lovely French military are operating for us down in sunny France. And what we need is a really high-tech antenna to pick it up. And here it is. Here's my one in my back garden. It's basically called a Yagi antenna. It looks a bit like a TV aerial because basically it is a TV aerial. It's the same design. If you look at your TV aerial, it's basically the same thing. It just has more of these things in the front, but it's basically the same type of antenna. This one was built from bits of wood, bits of electrical sort of conduit and junction boxes, and 1 3-meter length of copper pipe you can get from the plumbing section in B&Q or whatever. And we need a coaxial cable, which again I'll explain. It's an RG58 50 ohm coax cable. You can get those delivered off Amazon quite easily with the right connectors on. Again, all of the details are in the Sky at Night articles. If you can't get hold of plumbing pipe with the current difficulties that we've got, you could buy a tape measure. It just needs to make sure it's a metal, a steel tape measure. Some tape measures are fiberglass, they won't work. But if you can get a steel tape measure, you can actually substitute the copper pipe for a steel tape measure and just cut it up. Just be careful, because when you cut slices off out of the tape measure, the ends are really sharp, so you need to make sure you put some tape over them to stop yourself cutting yourself. But you know, I have built one out of plastic pipe and tape measure, which we take out to some of our events when we can run them. It's quite handy because it folds up, so the tape measure is nice and bendy. I can just chuck it in the back of the car without gouging the headlining out. So if you can't get a hold of copper pipe, as I say, be inventive. Any conductive metal will do, as long as it's rigid enough to stand out. It's straight. So you could use sort of people use aluminium wire to build aerials. You can use copper pipe. You could use steel tape measure, whatever you've got, as long as it's reasonably rigid and will actually stand up as an antenna. Okay, so really we'll just have a quick talk about how the antenna works. We won't go into too much detail here because it's quite an in-depth subject. But basically, a radio wave is just oscillating wave, an oscillating change in the electric field. So everywhere in the universe there's an electric field where there's positive and negative charge. And as a radio wave, or any type of light, because light is an electromagnetic wave, radio waves are electromagnetic waves, X-rays, all of those things, they're all electromagnetic waves. They're all basically the same thing. It's just how energetic they are, how light the wave is. So we have an electric wave that's traveling through space, and as the electric wave changes, it creates a magnetic wave, which is this red one at 90 degrees. So sort of imagine like this, traveling through space. You've got an electric and you've got a magnetic wave at 90 degrees to each other. So as the electric wave changes, the magnetic wave is created. As the magnetic wave changes, it creates the electric wave. So that's basically the electromagnetic force in a nutshell. And this basically allows light to propel itself through the universe under its own steam. So it's got energy, and as the wave oscillates, the electric wave creates the magnetic wave and vice versa, and it propels itself across the universe at the speed of light. That's a radio wave. Radio waves have 3 basic characteristics. They have their wavelength, that's the distance between the peaks. So if we just look at the electric field, the same is true of the magnetic field. We're going to look at the electric field. So imagine, and per that other diagram, we've got a magnetic field corresponding to this. The electric field, one wavelength is the distance between the peaks of each wave. So this is a wave that's 3 wavelengths long. Now frequency, we talked about frequency. Frequency is just the number of peaks that passes a given point in 1 second. So if we imagine 3 peaks, 1, 2, 3, past this point in 1 second, this wave would have a frequency of 3 hertz. That's 3 cycles per second. Now frequency and wavelength are just related. Frequency is just the speed of light divided by the wavelength, because that's basically the speed of light tells you how fast the wave is moving. The wavelength tells you how far apart the peaks are. So the frequency will tell you how many peaks can pass a given point in 1 second. Now this would be a very, very low frequency and possibly low in reality. So when we have radio waves, we're talking about 143 megahertz here. That's 143 million cycles per second. That's really lots of waves, but the wavelength is about 2 meters long, so it's longer than me. So it's quite a long wave. As you move up toward light, the wavelengths are much shorter. They're microscopic. As you move up to the X-rays and gamma rays, they get even shorter. And that's why things like X-rays can go through your body. It's because the wavelength is so short. There's so much energy that just blasts straight through. Whereas radio waves, they will travel through you, but they won't do you any damage. Light, interestingly, is absorbed by atoms because it's got the right wavelengths to do so. So we've got wavelength. The other thing we've got is the amplitude. That's the strength of the wave. So it's just basically how high it is. So this is a high amplitude wave. This is a low amplitude wave, but they're the same in all other respects. They've got the same frequency and wavelength. And the final thing we need to talk about is phase. And that's basically just whether the peaks of two waves that are going along together are lined up. If they're in phase, the peaks will be lined up. And if they're sort of not arriving at the same time, then they're out of phase. We'll explain why that's important in a minute. Okay, so how does an antenna work then? So we talked about an antenna. Basically, the antenna consists of a dipole. That's just basically two bits of conductive material, in this case copper pipes. I've just got two pieces of copper pipe here, and that's the middle bit of my antenna. We'll look at that again in detail in a minute. What happens is as the electric wave passes the antenna, it induces a current in the pipe. Now what happens is as the wave goes high on this side, you get a positive charge on this end of the antenna and a negative charge on the other end. And as the wave passes, the charges swap sides, backwards and forwards, oscillating as the wave goes past. And because you've got a positive and a negative charge at each end of the antenna, electricity and electric current wants to flow through the antenna from one side to the other. And as the charges change and reverse, the electricity wants to flow back the other way. You can see this, the amount of charge being generated goes up and down in time with the wave. And what we do conveniently is we split our dipole in half, we put our radio receiver in the middle, and that forces the electric current to pass through the radio receiver. And this is basically how we turn radio waves into electricity that we can then measure. Now, the important thing is that to pick up a given frequency, we need to make the antenna the right length so that the wave resonates. So if you have a guitar string, if you have a really long guitar string, you pluck it, you get a low note. If you move it, your finger down, you shorten the guitar string, you pluck it, you get a higher note. And that's basically because there's a wave making the string vibrate. And as the string vibrates, it has what we call a resonant frequency, depending on the length of the string. The same thing's going on here. Depending on the length of the antenna, it will resonate at a different frequency. In order to pick up the radio waves we're interested in, we need to make the antenna the right length, which is basically half the wavelength that we're interested in. So what we're interested in is the Graves transmitter, 143.05 megahertz. That's 143.05 million cycles per second. The wavelength of that is the speed of light, which is nearly 300 million meters a second, divided by 143 million cycles per second is 2.096 meters. So basically, to pick up this frequency, we need an antenna that is half of 2 meters, so 1.048 in this case. Now, the antenna we designed is a little bit longer than that. I think it's just because it's a pre-existing design that people modified. However, it works pretty well. It doesn't have to be exact, but the closer you get, the more stronger the signal you'll pick up. Okay, so that's the theory. If you're interested in this stuff, I'll explain where you can get more details on it later. Okay, so the final thing that we were going to talk about, because it's quite interesting for a number of things to do with detecting meters, is in and out of phase. We talked about whether wave peaks arrive at the same time. We have two radio waves arriving at antenna at the same time. They're in phase. The peaks 1, 2, 1, 2 are lined up of the blue wave and the green wave. Then the radio waves will add together. That's called constructive interference, and we get a wave that is twice as strong. Conversely, if the waves are out of phase, so the trough arrives when the peak arrives at the other wave, and vice versa at our antenna, then we get subtraction because this is negative, that's positive. You subtract that from that, and basically you don't get any signal at all. So phase is important. because it helps us to make a better antenna. The reason we need that is we need to put some extra elements on the antenna. So what we've seen so far on the antenna is that we have here, this is the dipole. As I say, this is basically just over 1 meter long, and it's in 2 pieces, which are half the length, and that's so we get the electric current flowing through some wires that we attach to each side. But if we put another piece of metal in front, another copper pipe or another piece of tape measure or whatever in front, that's a bit shorter and the right distance in front, what will happen is that this will absorb the radio waves coming from the transmitter, and then it will re-emit them in phase with the ones that are coming directly to the dipole. So it kind of strengthens the signal that's arriving at the dipole from the front, and at the back we have a longer piece of metal. These aren't connected to the dipole, they're called parasitic elements. They basically just receive the radio waves and they transmit them back, and the radio waves coming from the back are out of phase, so they cancel out. So what this does is it has the effect of basically anything that's in the direction the antenna's pointing is strengthened through this constructive interference, because these elements are set up to make the waves line up when they arrive at the dipole. Anything that's coming from the back that we're not interested in, interference from cars, from the house, from your microwave, whatever, will be out of phase and will actually be wiped out. So it blocks signals coming from behind that we're not interested in. Now, the more parasitic elements we put on the front here, the more directional the antenna becomes. In our case, we only want one because we don't actually want it to be too directional. We want to look at quite a wide area of the sky. But with a TV aerial, say, where we know exactly where the antenna is, you can see there's lots of those bits on the front of your TV aerial, so it's much more directional. You have to point it in the right direction. That means you get a much better signal. Okay, so building the antenna, all the measurements are in the article that you can download. It's really, really straightforward. Basically, we need a bit of wood. We need some electrical junction boxes, 3-way electrical junction box. You can get these from B&Q, probably hopefully order them online. They still doing deliveries. You need a bit of electrical conduit or any old pipe that will fit inside there, and you need what we call a compression gland, which is just kind of nut with a washer inside it that goes in here, and basically just super glue the 2 bits of electrical conduit and there's the compression gland in here. We seal all of this up because we don't want any water getting inside here, because it's going to be out in the wind and the rain. If we get water inside, it'll short the circuit out. That's not dangerous, but it will actually mean the antenna doesn't work. So we then just slot 2 pieces of copper pipe in through these pieces of ducting that we put on here. And what I've done, it's not shown in the article, it's a handy tip, so I put a little bit of wooden doweling in the middle just to hold them steady. We just need to make sure they don't touch each other so they don't short out, and that this distance is the right distance. Again, it needs to be 15 millimeters as per the article, so the whole dipole's the right length. Then what we do is we get our coaxial cable. It's a similar sort of stuff you use for TV aerials. So what you have is an outer shield, which is a sort of copper braid, and then you have an inner copper core, and you just connect the braid to one side of the antenna, you connect the inner to the other side of the antenna. It doesn't really matter which way around it is, it's not important as long as you're not shorting it out, and then that will actually pick up that oscillating electric current and send it down the cable. We'll see what we do with it later on, and we sort of basically seal it all up. We put a lid on here with a waterproof seal that it will come with, keep that all nice and waterproof, stop the wet getting in there. And then we just put the parasitic elements on the front and the back, and again these are just bits of copper pipe. They don't have to be electrically connected to this bit at all. You just basically clip them into some electric trunking. Again, it's all described in the article. Fix them, make sure they're the right distance apart. The measurements front to back are not the same, they're not exactly equally spaced. The lengths also need to be fairly precise. Doesn't matter if they're a little bit out, really, you can be a bit wonky. It doesn't have to be perfect, but the more exact you are, the more accurate it will be. The important thing is this bit is waterproofed, and we seal up the ends of this pipe here with some tape or rubber bung or whatever you've got, some hot glue, just to stop water running down inside. These 2 bits don't really need to care about those. They won't affect it if they get wet. And you can see the cables coming off here, and then there's a long bit of cable. We've got a connector on the end. It's called a BNC connector. Again, it's described in the article. This is how we're going to connect it to the receiver. It's on this nice wooden batten. I've actually then put an extra bit of bracket and brace here so I can mount it on a pole. One thing you need to do is make sure that it's strong enough to deal with any birds that may try to land on it. Most of us have to deal with hazardous pigeons, but they're generally not that heavy. However, our observatory, the North Essex Astronomical Society Observatory, the lady who owns the farm where we are, has peacocks, and we did have one of the peacocks, Stuart the peacock, landed on the antenna one day that we've got there and managed to bend it down so it was pointing at the ground. So you do need to think about making it strong enough depending on what kind of wildlife you've got flying around. Hopefully not peacocks, but you should be okay if it's just the odd pigeon or sparrow or something like that. Okay, so we just then need to mount the antenna somehow. The important thing, it needs to be at least half a wavelength, that's 1 meter above the ground. Doesn't matter exactly whether it's pointing up, down, it can be sideways, as we'll see, it can be straight up and down. It's not particularly important. I've put this one in my garden like this so that it's quite low so that we don't accidentally walk into the end of the pipe and poke our eyes out. If you're a bit higher up, it wouldn't be such a hazard. But it's just on a bit of a wooden pole I've stuck in the ground. It just needs to point roughly south, sort of southeast-ish. So basically, if you find the Polaris, the North Star, if you point it the opposite direction, you'll be pretty good. It doesn't have to be that accurate, and it doesn't matter whether it's pointing at the horizon or up a bit. Again, it's not that important. The main thing is it just needs to be at least 1 meter above the ground and fairly solid. Okay, so there's our antenna. The alternative, and this is the one the peacock managed to bend down. We used one of these satellite bracket arms that we screwed to the wall, and we just basically fixed it horizontally because it's quite a bit higher up, so no danger of poking your eyes out, but much handier for roosting peacocks. I actually used some heavier weight coax cable. There's stuff called RG213, which is much more expensive, but it gives you a better quality signal, but it's not that important for a home project. So about the antenna, now the main thing is to understand the sensitivity of the antenna. So what I've done here is I've used a bit of software to plot how sensitive the antenna is. So if you imagine, here's the antenna, here are the 3 bits of metal, here's the dipole in the middle, and it's pointing south, and this sort of weird flower thing down the bottom here is just a plot of how sensitive the antenna is in every direction. So where it's redder and further away from this green line, that means it's more sensitive, and where it's closer and sort of yellowy green, it's less sensitive. But the antenna is pointing south this way, so you can see it's quite sensitive on this side, not very sensitive on the north side, which is pointing back. But it's interestingly, it's not sort of uniformly sensitive. What we get these lobes, so essentially we get sort of different angles of sensitive, where it's more sensitive and less sensitive as we go up in the sky. Again, not too important really, as long as you've got it roughly pointing in the right direction. The main thing, again, I've got some software. Again, anybody who's interested, ask questions later. I'll try and explain it. But this is just a slice through that pattern that we saw. This shows the height above the ground. So I think we had it. I'm trying to see where we were at here. Roughly, the blue line is about 1.5 meters above the ground. My garden antenna, and this is the direction we're pointing in, left to right. Then as we moved it up to I think we moved up to sort of 4 and 6 meters. You can see it's much more sensitive once it gets further above the ground, and the pattern of lobes is the vertical slice over here changes as you get higher above the ground. That's less important. The key point is the higher up you put the antenna, the more sensitive it will be. And the reason for that is because radio waves are actually bouncing off the ground and up into the antenna, which interferes with the signal. And as you move further above the ground, you have less of a problem because they're coming from further away. So the higher you can get it, the better. But as I say, at least 1.5 meters above the ground. Now we've got to pick up the radio signal. So what we've got is we've got the radio signals coming from the antenna. We've got that bit of cable that we connected to the 2 sides of the copper pipe. It comes down into this thing here. This is basically what we call a software-defined radio dongle. Sounds really technical, but actually what it really is a repurposed digital TV USB dongle. So if you imagine you wanted to watch Freeview on your laptop, you can buy one of these digital TV dongles, you plug it into the laptop, plug it into a little aerial, and it'll actually pick up digital TV. You can use the same chips, and you can buy these online quite easily. Again, I'll explain where. Basically using the same chips that you use in a digital TV dongle as what we call a software-defined radio. That basically turns radio waves have come from the antenna in the form of electrical current into numbers that the computer can process. Now, the Sky at Night article recommends a dongle called the FunQ Pro Plus. It's about 170 quid. Don't buy one of those unless you're seriously into this. They are really good, but they're really expensive. You can get what we call an RTL 2832U SDR dongle for this, and it will work fine. If you don't know what I'm talking about, this one here is the one I use. It's called a New Elec NESDR Smart. Put that into Amazon. They're about 20 to 25 quid. You can get kits with all sorts of little bits of extra antennas and stuff for trying things out, but all you really need for this project is the dongle itself, and you need an SMA male to BNC female adapter. So basically, golden end of this adapter here screws onto this end of the dongle, and the silver end plugs into the BNC connector that's on the end of your coax cable that you bought, and that just connects the two together. And then the final bit here is a USB connector that just goes into your computer. I would recommend, if you can, using a USB extension cable. You can keep the dongle a fair way away from the computer, you'll get less interference. If you can't, don't worry about it, it will work. It just might pick up some signals from the computer. Now, in a traditional radio, we basically have to use all sorts of electronics to pick up the radio signal and do what we want with it. With software-defined radio, what we do is we just basically turn the incoming radio waves into numbers that the computer can process. And so rather than having to spend thousands of pounds on really expensive radio equipment that can only be used for one or two purposes, with software-defined radio for 25 quid, basically we can write programs that can do almost anything within quite a wide range of frequencies. I won't go into the details of all this, it's all on my website if you want to have a look at it. Basically all we're doing is we're chopping up the incoming radio signal that's been turned into electricity. We're just measuring it very, very frequently to measure the electric current, and we're turning that into numbers that go down the USB ports of the computer. Skip over a couple of these, quite technical. The final bit that we need then is the actual software in the software-defined radio. There are lots of software-defined radio applications. One called SDR Sharp is really easy, so it's SDR hash symbols, SDR Sharp. You can actually use that to listen to Radio Essex if you want. But the one we use is a program called Spectrum Lab. Again, it's explained about in the BAA website article. It's a free bit of software. It's quite complicated to set up, but there are good reasons why we use it. Fortunately, there are configuration files that you basically can download from the BAA site and from my website that will allow you to actually configure the software without too much messing around. There's a couple of steps that you have to follow that, again, are explained on my website. I won't go into all the details now, but basically it will configure the software to work. The software then basically takes the incoming signals that we've turned into numbers and processes them to show us the meteors. So what's happening is we're basically taking the complicated wave that's coming from the radio and we're splitting it up into lots of simpler waves. It's called a fast Fourier transform. Basically, any complicated wave can be made up by a much simpler set of waves that are joined together through constructive interference, and that's mathematically proven that's the case. At any wave, radio wave, kind of C wave, whatever it may be, you can analyse it and you'll find that underlying it, it's just made of lots of really simple waves that have all been added together. And what we're doing is we're taking a complicated wave and transforming it back into the simple waves. So what we can see here is this apparently complicated looking wave here is actually just made up of three really simple waves that are different frequencies. So this is a low frequency, medium frequency, high frequency wave. We add them together and we get what looks like a complicated wave, but it's quite simple. Spectrum Lab does that for us, and that's what we can see here. So basically this scale across here is the frequency. So these are low frequencies down this side. These are medium, these are high frequencies. This is actually BBC Essex. And what you can see across the top here is the radio wave that's been analysed in one instant. Now, it might be a little bit hard to figure it out, but if you remember back in the 80s, we all had these fantastic hi-fis with the graphic equaliser. You know, you'd be playing your favourite pop tunes on your cassette tape or on your CD if you were really posh, and the little lines would be bouncing up and down. It would tell you how loud the low frequencies, the medium frequencies, and the high frequencies were in the music, and they would change over time. This is the same thing, basically. It's much more granular, much more detailed, but it's just showing us how strong the signal is at each frequency at one instant, going across here. So maybe if we just quickly switch across to the actual software that we're using, I can show you. This is Spectrum Lab in action. What you can actually see is I've turned it on its side here. We've got high frequencies up here, lower frequencies down here. I think that's right. No, it's the other way around. I turn my head on the side here. 6, 9. Yeah. So low frequencies at the bottom, high frequencies at the top, and you can see these little lines bumping up and down, just like the graphic equalizer. That's basically telling us that how strong the signal is at these different frequencies at every moment in time. But in order to actually see what's going on over a period of time, we just keep plotting those signals on what we call the waterfall display, which is here. And basically this display scrolls down, or in the case of the one we're demonstrating live, across the screen. So this is in the past, this is now. Each time we analyze the radio frequency, many times a second, we just plot a line of the waterfall. So low strength, medium strength, high strength, and that just then kind of moves down the screen. So again, if we just go back, you can see it going on the live system here. We've flipped it on its side, so it's actually going across. So this is basically how the radio frequency is changing over time. This is 1 second apart. These little numbers down here are 1 second apart. This is how the radio frequency is changing over time. Okay, so if we go back now to presentation, that's the waterfall display. Now, why is that useful? Now we need to do a bunch of stuff to set up the dongle. I'll explain how all that works in the article. You can download it, but you basically need to install the driver for the dongle. You need to download some software to get a special file out of it, install that. And then basically you need to install Spectrum Lab, and then you basically download these configuration files from the BAA website and open them, and that will set the software up. There is a couple of steps, and again, all of this is on my website. Don't worry, I'll tell you where to find it, of how to actually set up the SDR dongle, the Neuelec, or whatever it is you're going to use, SDR dongle. There are a few steps you need to take in Spectrum Lab. It's a hideously complicated piece of software, but all of the steps you need to take are covered in detail in the presentation that you can download. It's not too difficult. If you get it right, all we then have to do is then put into this box in Spectrum Lab 103.500.000. That's actually the 103.5 megahertz. That's BBC Essex. If you get that right, assuming you're in Essex, of course, you should get a really strong signal scrolling down the middle of the screen. That's the FM radio transmission coming from BBC Essex. You see that, you know all your software's working, you're basically on the right track. If it doesn't work, then you might need a bit of help. So just go back and double check everything. Once that basic test has been passed, I'll just whiz through this. We then download another configuration file, so a different configuration file. This is set up to detect the Meteors from the Graves transmitter, so it's basically the same sort of thing. Just replaces the original transmitter. Again, comes from the BAA website. What we actually do is then we tune to a different frequency, which is 144.428.000. Actually put it in this box here. And that's actually a test transmitter that sits somewhere in the south of England. And it sends out sort of different tone, Morse code, beeping frequencies. So again, I can show you on the live view, hopefully, if I can get it working. And we go to the live view. I can actually got a convenient little button here to tune to the test beacon. And you can see I'm picking up this signal. Now, this is a signal that's been transmitted. It's specifically being sent by a chap down, so I think somewhere down in Sussex or Kent, somewhere like that, to help people test their radio equipment. It's quite a faint signal, so BBC Essex is really strong, so we know that's working, our basic setup's working. We can pick up this signal, which is much weaker. We should be able to detect the Meteors. All being well, you see that signal. You then need to then go and look at, as I say, if you've got that working, you should have that sort of your signal scrolling across the screen.
We then need to go and go to a different frequency. This is 143.048.000. That's the 143 nearly 43.05 megahertz signal the Graves space radar is transmitting on. The reason we go slightly lower in terms of the frequency so that ends up down here, then the transmitter is in the middle, and then we've got some headroom above. So basically we don't tune directly to the frequency we're interested in, we tune slightly below it so that it's in the middle of the screen, and then we wait. And eventually a meteor will come through the sky, and when the meteor comes through the sky, you won't pick up the radio transmitter, there'll be nothing will be going on, and suddenly you'll get a ping, and you get a little dash like this, something similar will appear on the screen for a few seconds, and you've detected your first meteor. Very satisfying when it happens. However, it's not a particularly convenient way of wanting to do lots of meteor measuring, because you don't want to be sitting there day in, day out waiting for meteors to turn up. So what we can actually do, again, I won't go into all the details, but within Spectrum Lab, in that configuration file that you loaded, there's what we call some conditional actions that basically sit there waiting for a signal to be detected, and when the signal's detected, it'll actually capture a screenshot and save it into your computer. So every time it picks up a meteor, it'll capture a screenshot and save it. So you can set your detector up, go to bed, go to work, do whatever, maybe not go to work these days, go to the garden, go to the lounge for a bit of a break, and then come back a few hours later and you should have a bunch of meteor captures in little screenshots in your screenshot folder. Without sit there. So that's why we use Spectrum Lab. It is quite complicated, but it does allow us to automate this capture of the data. It also logs that information into a text file, which we can use in a spreadsheet to analyze stuff, as we'll see in a minute. That's basically it. You may need to make some changes. That again, it's all detailed in the file that the document that I'll direct you to later. So when we get our first meteor, then what do we get? Okay, so remember again. This is scrolling down the screen, so the BAA setup scrolls down the screen. Typically the setups that we normally use scroll across the screen simply because the screen's wider than it is high, so it means we can see much longer time period on the screen if things scroll from left to right, or sorry, from right to left. But in the basic setup we go top to bottom. So remember, this is the transmitter frequency here, lower frequencies and higher frequencies to the left and right, and this is time, so this is like now, and this is several seconds in the past, and this is scrolling down the screen. What happens is we get a meteor and we get a ping. So this is one real meteor that I picked up on my setup when I first started out. I've blown it up down here, and you can see two things going on. First of all, you can see this streaky line. This is actually the meteor itself, the meteor head. It's a little grain of sand with a glowing ball of super hot plasma around it, bouncing radio waves, zipping through the atmosphere until it actually goes too low to be detected or it stops moving. That's the first bit. And then there's this big blob here, and this is actually what this is the trail that meteor has actually left behind in the sky. It can persist for several seconds, in this case a couple of seconds, but they can persist for much longer than that. So we can actually see the meteor, which is called the head echo, and we've got a static tail. We'll explain why the two things look different in a minute. Those are basically the two things to look out for with a meteor. We can also pick up the space station. Again, I was quite excited when I managed to do this for the first time. Again, remember this higher frequencies to the right, lower frequencies to the left. Recent time, further back in the past. This is the space station. It moves much slower than a meteor, so the signal lasts a lot longer and it changes frequency a lot slower. And you can also see, remember we said the Graves antenna is kind of scanning across the sky. So every time it scans across the space station as it's moving through the sky, we get a dash. And as the beam scans off, we get a gap. As it scans back on again, we get a dash, so on and so on. And this is it moving across our line of sight, then reaches the middle of our line of sight and then moves away again. So this is basically the space station being picked up by our meteor detector, which is after all what it's for. It's picking up satellites in space. Now, why does the frequency of the head echo change? You saw it change from a high frequency down to a low frequency. Well, what's going on is a thing called Doppler shift. So you may have come across Doppler shift if you've ever heard a siren of an ambulance or a police car. When it's coming towards you, it sounds higher pitched. As it passes you and starts moving away, it's lower pitched. And it's just because the source of the radio waves appears to be coming towards you. So the radio waves appear to be shorter frequency to you, the observer, as the source is coming towards you, and as they move past and move away again, the sound waves, the siren appear to get longer, so the pitch changes. And the same thing goes on with radio waves, but there's a slightly more interesting thing going on here. We don't necessarily see a meteor coming straight towards us or straight away from us. What can happen is the meteor is typically moving maybe a bit towards us, maybe a bit away from us, but it's actually moving across our line of sight. So it's zipping straight across like this. But the only way that something could move across our line of sight without getting nearer to us or further away from us is if it moved in a circle. You imagine a circle is basically a constant distance from a given point. This is us here. Meteors don't move in circles, they move in straight lines. So therefore, it must always be getting closer to us or moving further away from us, even if it isn't actually coming towards us, even if it's moving directly across our line of sight. It's getting nearer, 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 and further and further and further away. And there's just this one instant in the middle, at its point of closest approach, where it's doing neither. So this is what we call radial Doppler shift. So it's partly the line of sight effect as the meteor moves across your line of sight, and it'll also be an element of it whether it's coming towards you or away from you. The two things combined, we can't really separate them with the kind of equipment that we're using here. The two add up to give us this effect. So again, here's another one, an example. And again, this is scrolling down. I've shown it scrolling down the screen. So what we've got here is the meteor coming in. Unhelpfully, the higher frequencies are on the left here and the lower frequencies are on the right this time. So what we can actually see is the meteor moving across our line of sight, and the frequency of the reflected radio wave changes through Doppler shift because the meteor's moving, and then once it sort of stops, the meteor stops moving, it's either stopped moving or it's just gone out of our ability to measure it. We've then got the trail that it left behind in the sky. That isn't moving, that's just staying in one place in the sky, so we don't get a change in frequency, we just get this ongoing signal that's close to the transmitter frequency here. So overlay the two things so you can see what's going on here. This is the meteor, this is the head echo from the meteor. The trail is still in the same place, but because it's not moving, we get a long lasting tail. Now remember, you need to think about these things that we're getting on the receiver here. They're not pictures of the meteors, they're a map of how the radio frequency changes. So you need to have a think about how that works in practice. Now we can actually calculate how fast things are moving using a bit of maths. Again, I won't go into all of this now. It's all on the website if you want to have a look at it. Basically, if we transmit a frequency to an object that's not moving and bounce it back again using a radar, the transmitted frequency and the received frequency will be the same. We transmit it to an outgoing frequency to an object that's coming towards us. The object sees a higher frequency because it's all relative. It doesn't matter whether the transmitter's moving or the object's moving. It's just relative. The meteor will see a higher frequency, then it will bounce that higher frequency back towards us, and because the meteor is coming to us, we see an even higher frequency. So there are actually two Doppler shifts going on in this kind of reflection scenario. Here's all the equations for the members of the society who love this kind of stuff. So again, I'll direct you to where you can download all of this, but basically, if you know the frequency of the transmitter and the F0 and the frequency we receive back, and we know the speed of light, we can work out how fast the frequency is changing, and therefore the radial velocity of the meteor. So practically, here's my transmitter frequency, 143.05000, so basically 143.05 megahertz. At this point, the meteor is about 300 hertz, and it will start speeding up again as it goes past. That's simply just because it's that diagram for the circle. The distances will get slower. The meter's moving at a constant rate. Distances will get shorter less quickly as they get towards the centre, and then speed up again as they move out. Lovely maths. We can see this in action practically. Now here's a space station ping that I picked up in January last year. You can see the space station here being pinged as it moves across the sky, and I knew the timing of it. The timings are a bit out because of various computer clock stuff, but basically this is where the space station was. I think we can assume this ping is fairly close to the middle of this line here because it's sort of pretty much directly between us, the transmitter, and the space station. That's where it was. You can see the rate of change of the frequencies it moves across our line of sight. I then picked another one up a few days later, again plotted the line. If I overlay the two, what you can see is the angles of the lines are different, simply because the green one here, space station, is actually further away from the transmitter and receiver than the yellow one here. They're nearer, so the rate of change here is less than it is here, simply because the object's closer to us. If you imagine a car zipping along a road in front of you and it's half a mile away, it looks like it's moving quite slowly. If it's like 2 feet away, it's going to go straight across your line of sight. That's the same thing. It's just because the space station is nearer to us, therefore the frequency changes quicker. That Doppler, that radial Doppler effect. We could talk a bit about aliasing, but I don't think we're running out of time. It's all in the article. It's basically some interesting effects due to the way that we analyse signals. We won't worry about that. There are some other things we can pick up. So again, we've got the meteor coming in here. The trail should be static. It should just stay at one frequency. It's a bit off the transmitter frequency just because the tuning of these devices isn't exact, so the numbers on the scales don't always line up. You can see it's actually changing, and that tells us something about the trail. It must actually be moving, and it's probably because it's really high up and there's air moving that actually the trail's getting ripped apart and moved, so it's not staying in one place. You can also get some interesting effects where the strength of the trail changes and increases and decreases, just because we'll have different parts of the trail that are more reflective than other parts, and because the lengths that the signal is taking are different, the radio waves will arrive in or out of phase at the receiver, and therefore they'll actually start either strengthening each other or cancelling each other out, so you can get some really interesting differences in the strength of the signal. You can get lots of other interesting things going on. So here we've got 2 meteors. There's literally, this is not a sort of weird effect. There's literally 2 meteors coming down almost one after another. I've actually seen this visually a couple of times, certainly once in Australia and actually once in Essex as well, where there was a meteor went zipping across the sky, and within a second another one followed exactly the same path. Not surprising if you think about it. Meteors come from comets, and the bits that are blown off, they're all travelling on the same orbit. So you can imagine it'd be really easy for 2 little grains of sand to end up breaking off at the same time and travelling along pretty much the same orbit and just arriving a fraction of a second apart in the atmosphere. And that's exactly what we can see there. When we get meteor showers, we can get lots and lots of meteors in a very short space of time. So this was January 2019, the quadrantid meteor shower. Again, this is only sort of 20-30 seconds, 3 meteors in a few seconds. Then a minute later, we've got 3 meteors, even closer together. Same meteor shower, even more of them. And you can get this in a meteor shower. You can just get loads of them. Then you get a couple of other things going on. You can get what we call moon bounce. Exactly what it sounds like. If the moon is exactly the right bit of the sky relative to us and the transmitter, the radio waves can actually be reflected off the moon, and you can pick them up. The other thing you can get, which we do get quite a lot of, is a thing called tropospheric ducting, or a tropo. And effectively, the atmosphere acts like a lens, and if the conditions are just right, the radio waves will actually bend around the curve of the Earth, and you can actually pick the transmitter up directly when normally you can't. So you can get that effect, and then you just get this long continuous transmission for minutes or hours at a time sometimes. The other thing we can do, as I said, we put data into text files. Again, it's all kind of explained in more documentation online. We can actually count the number of meteors that occur every hour, and you can see it again in my live example here. This bit here, we're actually getting quite a lot of false detections at the moment, but just down here, I'm actually counting how many meteors I pick up during the daily meteor count. I've had 180 today. And I've had an hourly meteor count. It resets every hour. I've had 1 this hour so far. So every hour it counts, and it plots that data in a text file. That one, sorry. There we go. So basically what I did was I just took the number of meteors I detected by hour. So this is midnight. 1 a.m., 1 a.m. to 2 a.m., 2 a.m., 3 a.m., so on and so on. Middle of the night to 11 in the evening, middle of the day in the middle. I just took the number of meteors every hour and I averaged over 2 weeks the number of meteors I got in each given hour. That's the average of the number of meteors in 2 weeks was 49 in the hour after midnight over a course of 2 weeks and so on. And you can see something really interesting going on here once you collect a couple of weeks of data is you get many, many more meteors in the early hours of the morning, very few in the afternoon and early evening. And there's a good reason for that. It's because the Earth's travelling through space at 70,000 miles an hour. You imagine we're looking down on the Earth here. This is the day side and this is the night side, so this is where we're pointed towards the sun, rushing through space this fast, and we're rotating. What happens is that just like a car, if you're travelling along in a car in the summer, bugs will splat into the front windscreen of the car, but they don't splat into the back windscreen because you're moving away from them. So you're crashing into lots of bugs as you go forwards. The ones behind are getting left behind. That's exactly what's going on with the meteors. Basically, in the early hours of the morning and early part of the day, we're facing in the direction we're travelling through space. We crash into lots more meteors. Then at night, as we get into the afternoon and early evening, we're looking out of the back window of the Earth effectively, so only really fast meteors catch up with us. So if I go back, and you can see exactly that going on here. So there's kind of, if anybody says the Earth is flat, just get your antenna set up in the garden. You can prove that we're spinning around once every 24 hours, looking one way and then looking the other way, just through plotting this information. We can also then collect the number of meteors every day, and this is a plot of, again, some data in May 2019, and this is the day 1 of the month, day 2, day 3, day 4, day 5, and so on, across to day 31 of the month. Then this is the hour of the day from midnight through to 11, midday in the middle, and basically the colours, the red or the orange or red of the colour is the more meteors we get. What you can see is that in the early hours, sort of 5, 6 a.m. On day, I think it's day 5, 5th of May, we've got loads of meteors for a very short period, and that's because that's the peak of the Eta Aquarids meteor shower. And you can plot this data and you can track meteor showers quite easily with it. Now, you can collaborate. There are a number of websites online where you can upload this data, and one of the things they're trying to do, I don't know how successful they've been, is try and coordinate the data from lots of observers all around the world, and by working out where they are and how many meteors they detect, and therefore which bit of the sky is visible to them, try and work out if they can detect any unknown meteor showers by plotting the sort of where the antennas are out into space. We can work out if there's a radiant of a meteor shower that we don't know about. I'm not aware that they've been successful, but it's certainly an ongoing project that you can contribute to. As I said, the beginner spectrum lab actions are great for when you first getting started, but they're a little bit limited. There are a few issues with them, but I've done some stuff where I've made some more improved actions that work better. It's all explained on my website. So if you go to this web page here, www.blackwaterskies.co.uk, category radio, /category/radio, you'll find an article that explains all about the improved actions, and actually this whole talk and all of the notes can be downloaded from this link on that page. So don't worry, I've rushed through it all, but there's loads more information in the full piece. Download it as a PDF and it will explain everything to you in more detail. Again, and it's also got the link to the BAA website on that page as well, where you can get the starter information and the article for actually building the antenna. So www.blackwaterskies.co.uk, category radio. Alternatively, if you can't remember that, whatever, please either post the question on the YouTube stream comments, or go to our Facebook page, North Essex Astro, post on there, send us a message. We'll actually do our best to provide you with the information that you want and help you build your device virtually, as it were. Now, if you've got any questions, please feel free to post them in the comments or on our Facebook page, or just let us know through the comments. If you're a member of the Society, if you're a member of NEAS, you should have the details for a Zoom meeting. That'll be starting immediately this stream ends, which is almost imminently. So please jump on and we can have a chat, and I can give you any more information that you need. So yeah, that's basically meteor detecting. It's all, it's quite an interesting subject, simply because once you've built the thing, it's a little project to do around the house. If you're stuck in the house and you can't do anything, as I say, don't worry if you can't get to the DIY store. Pretty much everything you need can be got on Amazon, apart from the copper pipe. Get a steel tape measure, it will work just as well, and if not better, because it's actually easier and more portable. Give it a go, and it gives you hours of endless entertainment. I think you just leave it running, and you'll see what you get, and you'll learn a bit more about radio. You'll learn a bit more about meteors, and you won't have to worry about it being cloudy or rainy. So I hope you've enjoyed that. If you have, then as I say, please join us for more talks in the near future. We'll certainly have another one next month. We might do some live astronomy again. We may try to do some stuff with our solar telescopes, maybe, if we get some nice sunny weather and some interesting prominences. But that'll be at fairly short notice, I imagine. Again, follow us on Facebook, follow us on our YouTube channel, and we'll do our best to advise you and get you going in the right direction. So thanks very much for your time, and sorry about the technical problems at the beginning. I hope you enjoyed it.